Good afternoon. Today I'll talk about using satellite data for improving PM10 model outputs, and we test it over Chiang Mai City in Thailand. Before I go into that, I would like to talk about my institute. So it's the National Astronomical Research Institute of Thailand. Our headquarters located here in Chiang Mai City, and 50 kilometers south of the headquarters is the Thai National Observatory, which is located near the summit of the highest mountain in Thailand, Doi Intanon, around 2.5 kilometers above sea level. Aside from the Thai National Observatory, there are also regional observatories that are being built, and some have already been completed, like here, and here. So NARIC also plans to establish a National Research Center for Atmospheric Science, and this establishment project and infrastructure development has already started this month. And one of the first instruments that we would like to buy is a mini micropulse LiDAR to be situated in Chiang Mai City, which probably will be set up in January next year. So it can measure aerosol profiles of up to 10 kilometers. So for this work, the main motivation, at least for me, is so usually I was flying in from Manila to Bangkok and then to northern Thailand. And as I was traveling, I noticed when the aircraft was somewhere over here, you'd get something like this, and once you get inland from Bangkok to Chiang Mai, especially as you were going to land in northern part of Thailand, I would usually see this blanket of haze. And what was causing this, and try to understand how the mechanisms are happening that causes this phenomenon. So one of the main causes of this haze or this pollution is a shift in the crop in northern Thailand. So what was once were like forests have now been changed into corn plantation. And this corn is actually not used for consumption, but actually is used for animal feed. And what is left over after they harvest the corn, they burn, and this is usually the corn stalks and corn leaves. And this affects the health as well as the climate, particularly precipitation. It affects the delay and the timing as well as the amount of precipitation. So in order to understand this, first we wanted to know what we have right now. So we have weather models that you can go high resolution, that are fast, that are highly accurate, and they're fairly simple. And then there's a couple of models which can also be ran at high resolution. However, they would produce they would be ran slow. They will run slow, having a moderate accuracy, and this is primarily limited by the emission, the input emission that goes into the model, and it's also quite complicated. That's why it becomes slow. And what do we want? What we want is actually some model that is high resolution, relatively fast, moderate accuracy, and fairly simple PM10 model, which can be used like for forecasting these events. So the answer seems to lie in the parameterization. And so what is parameterization? So usually a model is divided into 3D grids, but some processes are quite too small to be resolved by the model. So what is the solution? The solution is to just find out the aggregate effects. And one example of or one parameterization that is commonly used in models is the microphysics. So microphysics pertains to how hydrometeors. So hydrometeors are ice crystals, water droplets, hail, graupel, how they are converted from one form to another, how they interact, how phase changes happen, latent heat release, and all that. So in this study, we used the aerosol-aware Thomson microphysics parameterization scheme. So the difference with the usual microphysics schemes is that it includes water-friendly aerosols, or these are some of sulfates, sea salt, and organic carbon, which are closely related to PM10, as well as ice-friendly aerosols, which are simply dust. So in the study, we used a weather research and forecasting model, version 3.7. So we used a 0.25 degree lateral boundary condition, and that allows us to model at a high resolution. So the first domain is 10 kilometers, and inside the domain is another domain of 3 kilometers. So we use the Moody's land use data set, which is newer than default USGS that is used in WRF, and we used to improve the surface winds, particularly in an urban environment. We used a 3-category urban canopy model, and then we used the Thomson aerosol-aware microphysics scheme with aerosol climatology. So we initialized the model by using the monthly aerosol climatology, which is derived from 2001 to 2007 simulations from GoCart. So GoCart is a coarse global atmospheric model, and we use this to initialize the model run. So we compared the model output to Pollution Control Department Air Quality Monitoring Site located in Chiang Mai City Hall for the period of April 10 to 20, which encompasses time before, during, and after Songkran. So as was mentioned earlier, so there's this no burning policy before April 15, which is the end of the Thai New Year versus Songkran. But after that, people are allowed to burn, but it seems also this no burning policy seems is not being followed, but it's a good start. So Chiang Mai City, as you can see here, is also in a situation in haze-prone environment because since it is like the second capital, second to Bangkok, so you experience a lot of rapid development and the topography. So it's located in a valley, and land use changes happening around it, like this proliferation of corn plantations around these areas. So we initialized with the aerosol climatology and compared to observations. So the observations are these black lines. So we initialize it here and let the model evolve. So just let the meteorology to take charge. So we converted also these aerosol number concentrations to PM10, so we can compare directly with the observations, and we find out that the model failed. The model was able to capture some of the variability, as can be seen here, but failed to capture some of these high PM10 events like here. So the Thai New Year or Songkran happens in this period from April 13th to April 15th. So the no burning policy is from April. So no burning until or after April 15, so which is from here to here. And that is why you can see this big, in the observations, big values of PM10 after the 15 that the model wasn't able to capture. So we tried to improve the model by, so from the monthly aerosol climatology, we added 10-day average prior to model start time. So we averaged MODIS brightness temperature data that has been average data, and then converted to aerosol number concentration using some empirical relationship between the brightness temperature and aerosol number concentration. So we initialized the model using that here, and then we came up with this blue line here. So as you can see, it was able to capture some of these high PM10 event, but still failed or overestimated this ones in the beginning, and but still failed to capture some of these low values of PM10, and still failed to capture this big PM10 event on the 16th. So also one thing to note, so actually the models actually are all underestimated the concentrations by around 50. So this line here will probably sit somewhere here, and we just added that into this plot. That's why we were just able to calculate the R and not much of the mean bias in RMSs. So so this is just some initial modeling experiment, and we plan to improve it more. So first by trying a different lateral boundary condition using ECMWF 0.7 degree or air intern 0.7 degree, and initial model runs seem to improve the correlation coefficient from 0.45 to 0.6. So it was able to capture some of this. Unfortunately, I wasn't able to show it because I had to rerun the model. It actually just finished yesterday. However, this one takes longer than usual due to additional nesting. So instead of two domains, we have 3. And it's not as updated as the previous one that we've used, so it won't be good for air quality forecasting. One other way we were thinking to improve the model is to initialize, do some daily updated initialization. So as you can see here, we initialize here, but if we try to initialize, let's say at the start of each day, see if it can capture more of these variations. So, and then we also want to add this offset into the boundary conditions and see its sensitivity to rainfall, also to compare with WRF-Chem. So I'll end my talk with this animation. So this is a 3D animation of the PM10 concentrations. So the bottom plane are the surface concentration. This is for the period of study, so the time before, during, and after the Thai New Year. The vertical planes intersect at the comparison side, and as you can see, so some things to notice. So first, you can see this clear gradient in PM10 concentrations from here to here. So that's your boundary layer at work, which traps most of the aerosols somewhere here around 3 or 4 kilometers. You can also see some transport that's coming from neighboring regions. That's going into there, going into the observation side, and so this transport seem to have combination of thermodynamic and mechanical forcing. So thermodynamic means the